And, and I'm going to share the screen. Okay, so I have a few things I want to do before we get started on today's lesson. Today's topic is chemical engineering and materials engineering, and I'm very excited to be teaching it to you. I think materials is just unbelievable. And anyway, so we're going to do some class activities, and then you'll have an activity to do outside of class as well. So, but I want to start, before we get into that, I would just want to do some kind of just catch up. So the first thing I want to look at is I want to see where we've been and where we're going. So remember class one, we just had an overview of the course and we started talking about the engineering disciplines. You might remember that we started making lists of all the different fields of engineering and the abbreviations, CE, Chem E, AE, ARC E, etc. And then we talked about the different industries that engineers work in and the different job functions like design and test and marketing. And then this is the class also that Prithvi did obscure engineering with you, where you picked an obscure field of engineering with a group and investigated it. And then class three, she went over the engineering design process with you and went through ocean, marine, and aerospace engineering. And I know you had Rob Weiland come and talk to you, and you did the boat project. And then class four, I covered that engineering education with you, and I've met with a little more than half of you. So if you haven't made an appointment with me yet, please do so. You go to our Confer Zoom page. Actually, let me just pull it up. Go to Confer Zoom. I'm going to open it up here. I'm still waiting to see something. Let's try it again. Nope. So here's Confer Zoom, and you go to appointment bookings, and you're booking an appointment with me during the slots that are available. So please do that. And okay, so I'm going to go back now to modules. So I've been working one-on-one with everyone for 30 minutes, 25 minutes, figuring out their field of engineering, setting them up with an engineer to interview if they don't have one, and then setting up their schedule. So that's what we did in those meetings. So that was engineering education. Then last week, I know that Priti did civil, structural, architectural, environmental with you, and you met Dave and Phaedra, who are our past students and husband and wife. And I heard they just moved to Hawaii. Very interesting. I think that you guys really enjoyed them, and you did a project. And so today we're exploring chemical and materials engineering. Next week, March 11th, you're going to be exploring mechanical and biomedical engineering with Prithvi, and you're going to be doing a biomedical engineering project in class. Class 8, you're going to be exploring electrical, computer, and software engineering, and you'll be doing that with Carl. Carl worked, as you remember from the first day of class, he worked in the computer industry for about 10 years before he started teaching with us. And then March 25th is spring break. And Sam, I know you're in high school. You're the only high school students in this section. Your high school spring break is probably different. So just remember there's no Cabrillo class that week, but when you do have spring break, we do have class.
Okay, thanks for the reminder. Thanks.
Yeah. Okay, class 9, April 1st, you'll have me, and we'll be talking about engineering employment and job outlook and salaries. We'll talk about other options besides going into engineering after you get an engineering degree, going into law or medicine or teaching or whatever. We'll talk about engineering ethics, meaning what is ethical behavior as an engineer in terms of using your knowledge in engineering to design things that are safe for people. And then we'll talk about engineering social justice, meaning when we design things, we know it has an impact on people, and we want to make sure that it has a positive impact on people. And then class 8, you'll have me again for agricultural engineering and industrial manufacturing. We'll get to virtually tour the horticulture facility up at Cabrillo, up on the hill, where they use a lot of agricultural technology principles in growing all their plants. It's really exciting. And then we'll also talk to a manufacturing engineer and we'll watch some videos and things like that. And then the last class, which is class 11, April 15th, and just a reminder, remember, this is a short course. It's only 11 weeks long. Our last class is on April 15th. Both Priti and I will be there. And you'll basically be talking about your your interviewing project that you did. You'll also be talking about the Mobile project, with which Priti will introduce next week. And we'll basically have a course wrap up. So, I'm going to stop sharing the screen now. And I guess now I'd like to find out from you um, if there's anything. I'm going to give you a couple of minutes to think about. Is there anything that you would still like to hear in this class that I didn't mention to you that we're going to cover? Because Priti and Carl and I are totally willing to tweak the class and put whatever you want in there. So I'm going to give you a few minutes. And I'm looking at the chat and I noticed that, Priti really likes you to sign in during the chat and then she checks attendance at the end. For me, what I do is, because I'm going around the classroom and asking you, I know who's here or not. So you don't have to put your name in for me, but it's fine if you want to. But so now think for a couple of minutes. I'm going to be quiet for 2 minutes. Hard to do, but I'm going to be quiet for 2 minutes and think about, is there anything else you want to get out of the class? And I would like you to write that in the chat so that everybody could see what else. If there's anything I did not mention that you want. Okay, I'm going to be quiet for 2 minutes. So you could write it in the chat and submit it as well, so I could just read them as they come in. All right, I think I'm going to stop. So it sounds like we're doing an okay job. At any moment during the rest of the class, if you think of something today or another time, just let us know, because we totally will put that in the class as well. So I'm going to go back to sharing now, and I'm going to go back to our module. And I still have had some students ask me, when are your office hours? How do I get there? I've also had people ask me questions about how to use Canvas, and I want to point you in the direction. So you see the modules right now. If you go to week 0, it says course overview and introductions. And here is where it gives information about Priti, Carl, and I, where our office hours are and how to get to us. So it's here. All those kind of questions that you're asking are all kind of orientation to the class, and it's all in week 0. Another question I've been getting is, well, I need help with Canvas, or I can't figure out how to do this in Canvas. Carl, Priti, and I are not the ones to come to get help in Canvas, because we know just a little bit more than you. You could realize that we just learned it last semester. So we at Cabrillo, there's tech support. And if I open this up in a new window, the Computer Technology Center is the best place to get help. And if you click on this link to the Computer Technology Center, there is a button to press to go onto a Zoom where people are waiting to answer your questions. So that's what you need to do. But there's also some other ways to get support in Canvas. And also, I want to really encourage you. Cabrillo is loaning out not just Chromebooks, but they're loaning out laptops with engineering software on there. They're loaning out headsets and camcorders and hotspots. So don't be shy. If you don't have the stuff that's that good, you go and fill out that form. Fill out the form to get what you want. All right. We, Cabrillo works really hard on getting money so we could support you. So take advantage of the support. Okay. All right. Also, let's go back to the zero module. Also student support. Some people have mentioned to me that they're having trouble in chemistry, maybe. If you open this up and the link, I'm opening up the link. And right here, the STEM Center is a perfect place to get help in any kind of STEM class. So any science, math, engineering class. Also in Watsonville Integrated Center is helping students as well. And the Math Learning Center helps in math here too. All right. So there's all this support out there. So make sure that you do use the support. Okay, I'm just following my list on what I wanted to cover.
Joanne,
So Cody.
Adam offered a suggestion in the chat about maybe discussing how engineers have to work with law.
Oh, okay. Yeah, we could do that. That'd be great. We could totally do that. Actually, I'll talk about it a little bit today because there's you'll see. So Cody, when we get to exponent, I have a slide that says exponent on it. I'll talk to you about it then, and I'm sure I'll remember. And then when we talk about post engineering stuff with the ethics class, we could talk about it then as well. Thanks, Cody, for seeing it because I can't see the chat while I'm doing this. All right. So the next thing I wanted to do is look at our homework assignment, not the one that was due yesterday or 2 days ago, but the one that was due a week ago, broadening your engineering education. I haven't read in detail. I did grade the homework you turned in on Monday on how complete it was, but I haven't read the details yet. But I did read the details of this, so I wanted to mention this. Some of you said that you really felt inspired from the videos. Some of you felt like you've seen a lot of inspirational videos and maybe they're not so helpful for you. We're always posting different things so that some people find them great. And, there's always going to be somebody who's not really that interested in what you're hearing. But we're just posting as much as we can to kind of help and support everybody. And what I wanted to talk about is what I saw coming up a lot is, being uncomfortable with failure. I'm going to stop this for a moment. And being uncomfortable with failure. And one thing I wrote on many of your homeworks is that failure is how engineers learn. Every time there is a failure, the uniform building code for building for civil gets changed. Specs get changed in every kind of design to make them better. So, failure is maybe not such a good thing when people are dying. But when people aren't dying, failure is a really good thing because you can learn from it. And I want to mention to you, Karen Groppe. I'll just write her name in here. Karen Groppe. She's, oops, spelled her name wrong. She's an engineering instructor at Cabrillo. And she's all about sustainability, just so that you know her. And she has office hours. And she teaches some of the engineering classes as well. Let me just post this, Karen Groppe. But what I love about Karen is she treats every bad situation she's in as a learning experience. And it's amazing to me because something will happen to me and I'll get down on it. And something happens to Karen and she thinks, well, what did I just learn from this? She always has such a positive outlook on life. And I just really appreciate having her as a colleague. And that's something to learn from. And I am, getting better at it, that whenever something bad happens, I think of what the good thing is. But she does it so naturally because she learned it, or she made herself learn it so long ago. I mean, some little things like my son spilled applesauce on the carpet the other day, and he was like, shit, he didn't say shit, and I was like, don't worry. What did you just learn? Oh yeah. Don't eat on a carpet. Don't eat anything liquidy on a carpet. because then you have to clean it. You don't want to clean it, so you don't eat it. But that's it. It's done. You don't have to be down on yourself for that. And I just think that, anyway, and a positive outlook is so good. I know that I wrote on some of your homeworks that attitude determines your altitude more than your aptitude. Let me say that again. Attitude determines your altitude, how far you go in life, more than your aptitude, how smart you are. If you have a positive outlook, on life, you're going to get to where you want to go in your goals, more so than if you were brilliant. Because a positive outlook leads you to just keep going. It's a growth mindset in a way. So I just want to encourage you to think about being positive all the time, trying, or what you're learning from. And of course, I'll get mad at something, and then I'll think about it and I'll be like, okay, and then get the support that you need or whatever. Okay. So I wanted to mention that. Okay. Next thing I want to mention, I watched Priti's video last week on civil engineering, and she had a lot of amazing or great slides of amazing civil engineering projects. But I want to mention to you that you don't have to work on an amazing civil engineering project just to be a great engineer. I mean, I want to mention a small project that is local projects that have been some great projects that you could be involved in. Because some of you maybe not want to do the, multi-million-dollar projects or multi-billion-dollar projects. You might want to do small scale projects. If you drive on Freedom Boulevard from Watsonville to Aptos, it's on the right side. If you drive on Freedom Boulevard from Aptos to Watsonville, it's on the left side. There's a housing development there called Parkhurst. I don't know if you saw it. It's a few miles from Highway 1. And the reason that it's called Parkhurst, which is kind of interesting, I like little tidbits in history. There used to be this person called Charlie Parkhurst a long time ago in our area. And the person was a stagecoach driver, a pretty rugged, tough stagecoach driver. And people would ask for Charlie to do the driving over other stagecoach drivers. And it winds up that not until she died did people know she was a woman. She dressed like a man, made believe she was a man, because if she was a woman back in that time, she wouldn't have been allowed to be a stagecoach driver. So she dressed like a man, make believe she is a man. She even, I think, smoked a cigar or cigarettes or whatever. She hung out with the men in bars. Nobody ever knew she was a man until she died. And they had to dress her in clothes, and they realized, oh my God, she's a woman. She's buried in one of the, I'm telling you a little long story, aren't I? She's buried in one of the cemeteries on Freedom Boulevard in Watsonville. One of the ones that have those big, I forget what they're called, those things, mausoleums maybe. Anyway, there's a housing development on Freedom called Parkhurst, and it's named after her. And the company in Santa Cruz, which used to be called Fall Creek Engineering, did all the development for that. And what was critical is that site of homes had to handle their own water, and they had to handle their own sewer. They couldn't draw on anything from the street, and they couldn't put anything in the street. So the engineers involved in this relatively small project, I don't know how many houses are up there. I never drove up, but they had to take care of all that. And it's really awesome because it's a sustainable project and it's a small project. I mean, another civil engineering project that I think is really interesting is there was a lot of car accidents on Main Street in Watsonville. People would speed down the street. So the civil engineers in the city of Watsonville redesigned that street, and they have now, instead of just two sidewalks on the sides, the sidewalks actually butt out. So they kind of narrow traffic so they can't speed anymore. And there's this local artist who did these beautiful mosaics on the sidewalk there to represent all the immigrant groups that came into Watsonville. It's really a cool project. Other projects were about the '89 earthquake. In Santa Cruz, they had to rebuild most of the buildings in downtown Santa Cruz. They had to rebuild some of the bridges from Capitola to Watsonville. So anyway, there are small projects to get involved too. You don't have to be on huge projects. So I wanted to say that. Okay. And then the last thing I want to do before we start our talk is I want to mention some tidbits. And I know you've met Kalika, Phaedra, and Dave. And you will today meet Maseo. He's not live, he's on a video, and you're going to meet Isadora on a homework on a discussion. But it's funny because most of these people found their partners at Cabrillo. Dave and Phaedra came to Cabrillo and they're married. Kalika met Jack on the Engineering Abroad program, who's also a past engineering student. They're married. And Isadora met her husband in Engineering 5, Johnny, and they're married now. So it's kind of cool. Anyway, we're very connected, you could see, with our alumni, and I'm just getting chills just thinking about them. But we really love our students, and I'm glad that you're here at Cabrillo because we're going to love you too. Okay, so now we're going on to the topic for today. So I'm going to go back in and share, or actually, maybe I should just ask questions first. Any questions before we start our chemical engineering and materials engineering topic? I'm looking at the chat to see if anything. Yeah, so Adam said he'd like to hear about engineering and global and working on policies and regulation and law. So we'll talk a little bit about this today, but then mainly we'll be talking about it during that engineering and employment part. Okay, so and some of you may have just come on. Definitely watch the video, the beginning part of the video of what I covered so far that you missed. And also I mentioned that you don't really have to write your name in the chat for my classes because I go around the room and I ask you questions, but you could do it if you want, because you're probably used to it because you want to do it with Priti. Okay, I'm going to share the screen now. And I'm going back to the modules, and I'm opening up class 6, which is the module we're doing today. So basically, remember when I did engineering education? Let's just go back to engineering education. And I mentioned to you that I put every single thing separate, listing separate. And I saw some of your heads like nod like that. And some of you probably prefer things all together. So I did it differently this time. So in class 4, I listed everything separately. And in class 6 today, I basically, it's all in a PowerPoint slide. And then I have 2 things, an activity that's separate and then 1 video that's separate. So I'm doing it differently so that I could determine from you what you like better or what the majority of you like better. So then I could, when I do the next 2 lessons, I could figure that out. So what I'm going to do is I'm going to stop sharing now because I'm just going to pull up the PowerPoint instead. And now I can share the PowerPoint because I have to share it separate. And let's move these things out of the way so I could start the slideshow from the beginning. And how does everybody see this pretty well? Do I have a thumbs up or something? Again, I can't see the
we can see
chat.
it.
Yeah.
All right. Okay. So we're covering mechanical, chemical and materials engineering. And now why do my down arrows, okay, I have to do it like that. All right. Okay, so this is not going to be a technical talk. I'm going to talk about it on the surface. I guess I'd like to know, how many of you have taken chemistry? I guess I should stop sharing for a moment. Could you give me a thumbs up if you took chemistry, even if it was high school chem? 1, 2, 3, 4, 5, 6, 7, 8. Okay, well, 3, 4, 5. So it looks about half of you. Okay, so the half of you that have had chemistry, whether it's high school or college chemistry, I might be talking a little bit too rudimentary, but those of you who haven't had chemistry, you're going to be fine following along. So don't worry. All right. So I was hoping I could click it down, but it's not allowing me. Oh, I guess I could do this. Well, I would rather do this, the larger slideshow. It's better when it's bigger, right? You guys?
It's fine for me, but I'm on a desktop. It might be different for someone on the phone.
Okay. Well, how does this look, or should I, does this look okay? Because then I could see all the slides on the side. Because for some reason my down, oh, there, my down arrow is working now. Let's see, I'm going to go back to slideshow from the beginning. Okay, here. Okay, I'm going to use this. All right, so this is called the periodic table, right? It has all the elements in here. Here's hydrogen, lithium, magnesium, sodium, chromium. Here's iron, right? Here's copper. Okay, so all these guys are arranged by the number of protons. So they all have a number. Like this is boron, it has 5 protons. And as long as it's not an ion, it would have 5 electrons too. This is fluorine. So this really, actually, you know what? I can't see my notes that I've written, so I'm actually going to keep it like this. So I'm hoping this is okay for you guys. Okay. So everything in nature, everything natural and artificial, all has chemicals in it, and chemicals are made up of atoms. And this periodic table is just showing that arrangement of atoms, and the numbers, again, I said are the protons, but as long as it's not an ion, these are also the number of electrons. Remember, an atom has a nucleus, and there are protons and neutrons in the nucleus, and then outside of the atom are electrons. And those guys want to be bonded, and they want to fill up their orbitals. Orbitals are just kind of areas around the nucleus that get filled. So if we look at an example of sodium, I could tell you that sodium only has 1 electron in its outer shell. And chlorine needs 1 electron in its outer shell. So sodium and chlorine love to come together, and NaCl is table salt, and they're bonded by an ionic bond. So whenever these atoms come together to bond, they bond by different kinds of bonds. There's ionic, covalent, metallic, van der Waals forces, other secondary bonds. There are all these bonds, but you don't need to know all these terms. The idea is that the goal in chemistry is really to come to the lowest energy state. And when electrons are in the outermost shell and they're not filled, they're freaking out. There's so much energy. And when they bond with another atom that's freaking out, when they come together, they get more calm. I guess maybe it's when you find your partner, maybe, and get married. You kind of like want to find somebody. This person wants to find somebody. And then when you find each other, it's kind of a little calmer. Okay. The atoms in this last shell are completely full. So they're very happy and they're low energy. Okay. So let's go to the next one. So not only is it important to know that everything is based on chemistry, but take a look at these. These are 6 different kinds of chemical arrangements of carbon, hydrogen, and oxygen. So they all have carbon, hydrogen. I'm so excited. I'm like talking too fast. They all have carbon, hydrogen, and oxygen, but notice they have different amounts. Not only do they have different amounts, but look at vinegar, look at alcohol and antifreeze. The way they bond is different, and their 3-dimensional arrangement is different. And basically, how they bond and what their composition is and how they bond really determine how something behaves. Vinegar and alcohol, and this is drinking alcohol, not isopropyl alcohol, and antifreeze, they all behave quite differently, right? Right? They're all different. You could drink vinegar, but you can't drink antifreeze. But they're basically made of the same thing, but different amounts of it and different compositions. In fact, you might have heard of graphite. Graphite's what's in a pencil. You know, you might say, oh, it's a lead pencil, but it's not lead. There's no lead in there anymore. I thought I had a pencil here. I can't find it. Anyway, graphite's in a pencil, and diamond is a diamond, right? Both of these are made only of carbon, but they're very different. Graphite, lead pencil, you could break it so soft, you could get it on your fingers. Diamond's one of the hardest materials, right? So because graphite and diamond, both, even though they both have carbon, they have the carbon arranged in different ways that give them different properties. So it's important whether you're going into chemical engineering or materials engineering to understand both of them are really based on chemistry. Okay, so now that was an overview of chemistry that we needed to have a little background before we went into chemical and materials engineering. And first we're going to go into chemical engineering. And what I did is I wrote the Technical Society of Chemical Engineering. It's called the American Institute of Chemical Engineers. And it's a national organization. I believe it's either the homework you just handed in on the next homework, where you're looking at technical societies. And technical societies it's an organization, a national organization of all chemical engineers. So chemical engineers join these organizations so they could go to conferences and talk to each other and find out who's working where and what do they do for their job. And maybe I want to find a better job. But what's also cool about technical societies is these societies also are at the universities, and you could join as a student. And as a student, typically you could join these societies for free, or maybe $10 a week, $10 a year, sorry, or $20 a year. And what's really cool about it is you get a monthly magazine that talks about new innovative chemical engineering projects. So when I was working as a civil engineer, I joined ASCE as a student, and I would be looking in that magazine all the time and looking at jobs to just see what the future holds. And when I was a civil engineer, I still belonged to the organization. And then when I became an engineering educator, I joined ASEE, American Society of Engineering Education. And you heard of that group, ASEE, 2 weeks ago, because all the engineers by the numbers data you saw, that was all produced by ASEE. So it's a really great thing for you to look up if you're interested in chemical engineering and join that society, or join whatever technical society for the engineering field you're interested in. Okay, next. Now, the next is an overview of chemical engineering, and we're only going to watch 7 minutes. So I'm going to kind of change it up a bit. We're going to watch some videos. I'm going to talk. Well, I'm going to talk. We'll watch videos. I'll talk. We'll do a project. I'll talk. We'll watch another video. So right now we're going to watch a video. So I am going to stop sharing for a moment, and I'm going to pull up this video. And now I'm going to share this video. And again, we're only going to watch the first 7.5 minutes. So I'm going to start it.
As an engineering discipline that involves designing processes to transport, transform, and produce materials. Chemical engineers have knowledge of physics, chemistry, biology, and math to design these processes.
Can you turn it up a little, Joanne?
Wide range of careers they can go into, which is definitely a perk of this major and one I want to talk about first. So for one, you can go into biotechnology and the pharmaceutical industry, where you design facilities that use enzymes and microorganisms to create new drugs. Companies like Pfizer or Merck are examples of this. You could go into environmental engineering applications, in which they try to reduce the volume of pollutants that enter the air, waterways, and soil. Think of catalytic converters on our cars, which need to be designed to minimize the amount of harmful material that is released. Catalytic converters are essentially just small chemical reactors that aim to reduce the amount of harmful substances released by the car. You could also go into semiconductors and electronics, which is actually very big for chemical engineers that lots of people don't realize.
Something that was once done only by
What the hell is
men will
that?
be the key to taking years off your appearance. Believe it
It's
or
an
not,
ad.
this isn't some
Okay.
Think about companies like IBM and Intel that design and manufacture microchips and other computer parts. You'd think these places would mainly hire electrical or computer engineers, but these places are huge on hiring chemical engineers. To manufacture these microchips, they start with large silicon crystals that are then cut into wafers. Then the transistor architecture is pressed onto this material. The transistor design is left for the electrical or maybe computer engineers, but the framework or foundation and the process that makes it happen is what the chemical engineers do. Overall, there's a lot of chemical design and chemical processes involved in making those chips. You could work on industrial chemicals like detergents, soaps, and cosmetics, like at Procter & Gamble or Johnson & Johnson. Most people don't realize just how much work goes into that one bottle of detergent you get from the store. You could work on food production like at Nestle or Kraft, or wine and other alcoholic beverages like at Budweiser. You could work in petroleum engineering like at an oil refinery that turns crude oil from the earth into gasoline, diesel fuel, heating oil, etc. You could work for companies like Shell or Exxon, which hire a lot of chemical engineers. So while a petroleum engineer may specialize in designing the equipment to extract the crude oil from the earth, chemical engineers may focus more on designing the equipment that implements the chemical reactions, which turn the crude oil into something useful like gasoline or diesel oil, as you can see in this picture, which would be found at the refinery shown above. You could work in alternative energy. For example, there's solar cells, which involve chemical processes to be designed like the microchips I talked about earlier. Or you can work on fuel cells, which convert chemical energy from a fuel into electrical energy. These can be seen in cars, planes, boats, submarines, and more, and you learn how these work and how they are made. And there's even more careers you could get into. But now let's talk about specifically what the chemical engineer does in these fields. Like I said, they make food or alcohol, but how? What exactly do they do? Well, chemical engineers focus mainly on scale up. This is a term you'll hear a lot if you've done research, as in taking a small reaction and scaling it to happen on a larger scale. This is important and is a main difference between chemical engineers and chemists, which I'll get into later. So maybe a new liquid soap is designed in a lab. That's the small scale, just using typical equipment. So now you have the formula for this new soap, but how are you going to produce large amounts of it in huge reactors, big enough to even fit a person? This is the large scale because it needs to be shipped out in thousands of bottles. Do you think you just add more chemicals than do everything else the same? That's not how it works because problems will occur if you do this. So chemical engineers focus mainly on chemical process design, like designing a processing plant, or a big one for them is designing chemical reactors, which is where the large-scale chemical reactions take place. And of course, there's more equipment than what I've shown so far. But let's look at an example of manufacturing beer, which I said is something chemical engineers can do. Well, there are people out there that brew beer at their house, but this is the smaller scale. Chemists or chemistry majors could understand on a deeper level the chemical reactions that take place during this process and could look for ways to improve it. But if we look at a company like Budweiser, they have to produce large amounts of beer. So they don't have some home station. They have large reactors that make the beer, and this is where the chemical engineers come in. You can't just take that same at-home formula and make everything bigger. Lots more has to be taken into consideration.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
So to make that reactor, you have to size it properly. You need to design the cooling jacket, which is a layer of cooling water that surrounds the reactor to maintain the proper temperature, because you don't want it to get too hot. You need to design all the safety components, such as the temperature sensors, the flow sensors, and the control systems that go along with them. If the temperature sensor says it's getting too hot or cold, the control system tells a valve that is letting in steam to open or close based on the temperature. This seems like something an electrical engineer might do, but chemical engineers will see this as well. You'd also have to design the pressure release valves to maintain proper pressure within the reactor. On a small scale, you can use a simple valve, but with a huge tank, there needs to be a very specific pressure release valve. Also on a small scale, you can just pour in materials like the yeast to make the beer. But on a large scale, you have to design the piping that delivers the material, because if you deliver too much too fast, then problems can occur. And this is why you do have to understand chemistry, because you have to know what's going on in the reactor so you can apply the engineering principles to design it safely. How fast a reaction happens has to do with kinetics, which I'll talk about soon. But did you notice something about everything just listed? It's really not directly chemistry related. You have to understand the chemical process going on in the reactor that makes the beer, but there's so much more like the valves, controls, pipes, sizing, etc. that isn't directly chemistry related. And this is where chemical engineering and chemistry are different. A chemist would not be doing everything just listed, as that contains a lot of engineering rather than strictly science. So to be more specific, a chemist or chemistry major learns more about the reactions on a smaller scale, and they have a deeper understanding of those reactions. So if you want to be the person who puts on a lab coat and works solely with chemicals, chemical reactions, formulas, etc., then you probably want to major in chemistry or maybe even biochemistry if you want to look at the chemical processes within living organisms. But you would need to get a master's and even consider a PhD. Those are the people who are designing the new types of medicines, gels, detergents, and so on. But then they usually hand off that information to the chemical engineer, who then scales up that process. And they design the plant, the reactors, and so on, where that same chemical reaction will happen, which is why they still need to have an understanding of the chemical reactions. But much more needs to be accounted for. Now, I will say that this isn't always the case, so don't take it as a guarantee. There are chemical engineers who do work in a lab and work on chemical design like a chemist would. But usually they work on more of the large-scale plants and reactors, which involves so much more than just working with chemicals. Now, I want to briefly go.
Okay, I'm gonna stop sharing for a minute. Okay, so and now I'm gonna go back to my slide. Okay, and I noticed that, let's go back to this slide. So they were talking a little bit about chemical reactions, right? And we learned that we're always moving in a direction of something that's lower energy and more stable. And you probably have, at one time when you were a kid, maybe combined vinegar and baking soda, and you got this foamy mess. I mean, probably many of you did that volcano project in science or something. Well, what is happening? They're combining acetic acid with sodium bicarbonate. And when you combine two things, again, everything wants to move towards lower energy. This is lower energy. It releases carbon dioxide and it releases water, and that's what the foamy mess is. But the end result of putting these two together leads to this and this. And this, the arrow is like that because these two things together don't want to stay separate. They want to be together. So when you look at chemical engineering, you need to understand these kind of chemical reactions in such a way to know, well, what is, you're really working backwards. What do I want? Do I want beer? Do I want a soap? Do I want what? What do I want? And in order to get what I want, you figure out what you need to put together. Okay? All right. So we had a little bit of an overview of chemistry, and now I want to talk a little bit. He did talk a lot about the industries that hire chemical engineers, but I just want to go over it and show you the percentages. So working directly with chemicals per se is 23%. And then working in electronics is about 16%. Working in fuels, petrochemical, 16%. Working in food and consumer products around 11%. Materials, 3%. Biotech and pharmaceuticals is about 9%. And then there's some other here. So I wanted to give you an idea that what I love about chemical engineering is you could work in so many different diverse industries. It is the most diverse industry. I mean, the most diverse engineering field, but you have to love chemistry. So if you love chemistry, this is an option for you. If you just like chemistry so-so, but designing all the piping and stuff for scaling up like they talked about in the video sounds interesting, well, then chemical engineering is for you. But if you really don't like chemistry that much, it's probably not the field you want to go into. He did mention some specific products, and I want to talk a little bit about them because they are close to home. Semiconductors, he showed you this. This is a silicon wafer. There's a lot of chemicals on top of this. And you see the little squares here? They're all repeating patterns, and you cut those little things up, and they're called chips. And they get embedded inside this whole piece. And this whole piece has metal leads on it. And then it's encapsulated with either a polymer or a ceramic, depending on how hot it is. You probably know that a ceramic cup could handle heat more than a plastic cup. So that's what determines how hot does this get, and that's what this outside is. So even though chemical engineers are working in the semiconductor field, a lot of them do, and that's where a lot of you will get a job over the Silicon Valley if you choose to stay close to home, and you might be working with materials engineers as well. Okay, next one. Chemical engineering and fighting COVID. This is very close to home. Chemical engineers, again, I mean, chemists have been involved in this, but chemical engineers have been involved in scaling up. Who is making large containers of and producing large containers of hand sanitizer? It's chemical engineers. Here's a scaled up model. Here's a vaccine. He mentioned Pfizer. You heard of Moderna. You heard of J&J, Johnson & Johnson, which he talked about as well. This is really close to home for us. If you want to be working in the pharmaceutical, helping people, chemical engineering is great. Another one he mentioned is solar companies. So if you want to work in environmental and sustainable work, this is really great for chemical engineers too. Future of battery technology. There's a company in Watsonville called Sierra Therm that works on making solar panels. And they hire engineers, and they just got bought out about maybe 5 to 10 years ago by a German company, but they're still here in Santa Cruz, and they hire some of our graduates are working there. Let's see. Another slide, pharmaceuticals and cosmetics. He mentioned that. This is all involving chemical engineering. Food production, I picked some food of engineered food, right? Beyond Burger, Impossible Burger, Awesome Burger. I don't know if you probably have heard about these. I don't know if you've tried them. So far, I've tried the Impossible Burger, and it seems very much like meat. In fact, it's like too meaty for me, but all the cereal, it's all processed. Here's some veggie chicken strips. So this is all engineering as well. Chemical engineering. And then something these are some slides of things that were exciting for me. There's something called biomimicry, and it means just that. It's mimicking biology or mimicking nature. You may or may not have heard that Velcro, which you know what Velcro is, it's plastic. It was designed by mimicking something in the environment where they attach themselves to things. So animals, small amoebas. Also, a beach shell is very hard, but it's very strong as well and tough. Tough means it could take a lot of energy. You could throw the shell against the wall and it probably won't break. And that is not easy to come by in regular materials. Regular materials, if they're hard, they're usually brittle and break. And we'll talk about materials when we get to the materials topic today. But this is a really great thing to mimic from nature because it has combinations of properties that we don't really get in synthetic material. Another thing I learned, I traveled to China to meet a friend, and a friend of a friend was a petroleum engineer by a master's degree, and the bachelor's degree was chemical engineering. And what he loved about working in the petroleum field is he got to do a lot of international work. He lived with his family in the UK, then for a few years, then they lived in the Middle East for a few years, and then they were living in China because petroleum products are all over the world. So if you like international work, and he brought his family, so his kids were raised from like 0 to 8 in 3 different countries, really cool. And then they came back to the United States. Another thing is I remember that one of you is interested in fire protection. And when I went to the American Institute of Chemical Engineering Society, Technical Society website, they had this magazine, which is all about fire code protection, fire code requirements for fire protection. And I hadn't put it together, but when I saw this magazine, I was like, oh yeah, of course. Fire protection is under chemical engineering as well. So it may be that if you don't want to get a bachelor's degree in fire protection, which I'm not quite sure where they have that. I know there's no bachelor's degree in California. Maybe there is somewhere else, but certainly a bachelor's degree in chemical engineering. Okay, so that's our overview of chemical engineering. I'm going to pull up the materials engineering slide. I'm going to stop sharing and just check in with you to see if you have any questions about chemical engineering. So in terms of the local area, solar production is done in our area. A lot of semiconductors is done in our area. In Gilroy, you know about garlic, right? Gilroy garlic. There's a spice company over there that hires chemical engineers. I think it's Schilling. And you know, anytime you cook, you're probably using spices in there. Some of them are made from Schilling. Also, the idea of scaling up, you know, I don't know if you've ever cooked a meal for your family and then had 20 family, like try to cook for a wedding. You know, like they said in the video, you can't just scale up. You can't just add 1 teaspoon of salt and now multiply it by 20 or something. You can't just scale it up. It's not going to taste good. There's a chemical process that's going on. So even if you like that whole idea about cooking, that's also chemical engineering. Okay, I'm going to shut up for now. And okay, so Ulysses asks in the chat, are polymers the lead in materials engineering? We're going to talk about materials engineering in a little bit, and I'm going to start asking you guys questions, but there's so many new polymers now. Polymers are big. Ceramics aren't as big, but glass is still big. And what else is big is composites, which is a combination of materials. You could get a polymer engineering degree from schools in Massachusetts back east. Okay, other questions about chemical engineering? Crystal.
Yeah, I have the impression that environmental engineering, most of it has to do with chemical engineering. And I just wonder, I haven't taken all my chemistry classes yet that I need to. I remember hearing a student realize they didn't really want to major like in chemistry, for example, because they had spent all this time in a lab and they're like, I'm sick of a lab. I don't want to spend any more time in a lab. And I just wonder, I'm like, I don't want to end up in a lab all the time either.
Yeah, right. Okay.
It's really hard to find specific information, examples of different kinds of environmental engineering, because everything that I find is just all general.
Yeah.
So
This is good, Crystal, for me to write down. It sounds like you would like to learn more details on environmental engineering, and there are a number of you. So let me make sure that I take some time, of course, not today because I didn't prep for it, but let me find more information on environmental engineering. Like, just like I did that little spiel on chemical engineering, let's do something similar in 15 minutes for environmental engineering. Does that sound good? But Crystal, good? Is that would that be helpful?
Today or
No, I have
no?
to prep for it. But what I
No,
can
let's
say,
talk about it another time, I guess.
yeah, what I can say though is that chemical engineering, you're going to be using chemistry, you know, environmental engineering, you're going to be using chemistry a little bit, not that much. Environmental engineering is more closely tied to civil engineering. Clean water systems.
There is some environmental engineers like that have to deal with how do you get rid of or treat contaminated soil. And they have
Yes.
to do.
Yeah. So one example is there's something called bioremediation, where if you have contaminated soil, I worked on a project. You spread the soil out, you introduce these microbes. The microbes like to eat that bad stuff, and then you test it, and then it's clean and it goes right back into the environment and it's fine. So there are processes already developed. It's not like you as an environmental engineer have to say, what do I need to put some carbon and oxygen in this? There's already, you know, some of it is cookbook. It's already there. But you have to be willing to deal with chemistry, but you don't have to love chemistry like you would if you were a chemical engineer.
Okay.
So I hope that helps a little bit, but I want to get more in detail on it in another time. But I wrote it down for something for me to prep. Okay, any other questions about chemical engineering? Come on, give me another question. There's like 25 of you. One more.
Joanne?
Yes, Adam.
So I know I'm going towards aerospace engineering, but could you talk a little bit about materials engineering when it comes to things that go into space?
Sure. I don't know a lot about materials that go into space, but what I can say is if you want to be a mechanical or an aero engineer, if you want to be designing things that you touch and you have to choose materials, typically you could call up a company that sells materials and they could walk you through which materials would be best for your purpose. So not all mechanical and aerospace companies have materials engineers there because they might not need that. They might not be enough work for a materials engineer. Now, maybe in aerospace, because it's so highly technical, it's a different environment than we're used to. Those kind of companies probably do have material engineers to work on a team with aerospace and mechanical engineers to come up with the right material to use. But a standard mechanical engineer, that wants to make something, they could call up a manufacturer and say, hey, my product is going to have this, it's going to be subjected to this temperature, it needs to be molded, what material would you suggest? And then a company will tell them. Okay, so I don't think that's completely answering your question, Adam, but I don't know exactly what materials are done in space, but what I think, Adam, did I set you up with someone?
Oh, yes, you did.
Who did I set you up with? Chris?
No, I think
Mario?
it was Mario. Yeah.
Mario. Okay. So you're going to be talking to Mario and he works at Lockheed and he designs things like I know he was working on satellites for a while. I don't know what he's working on right now, but he would be a great person to ask that question because he's had to make choices on materials. And if he can't answer it, he could put you in touch with another Lockheed person to do that.
All right,
Okay.
awesome. Thank you.
Okay. Yeah. So the purpose, I guess, of this class is kind of to give you an overview and kind of put your technical tentacles out somewhat. But once you want to go really deep, you're going to have to ask the engineers that I set you up with. Okay. And if they can't answer it because their tentacle is deeper here, not here, you have to ask them, can you put me in touch with someone who could answer this question? Okay. All
Okay,
right.
thank you.
And then depending on your interest, like for you, Adam, if you want to work on certain, materials that are in, space, then you would want to transfer to a university that has an aero program where professors are working on materials in space. So you're going to be doing some investigation and that will come into play in deciding which university you want to go to or not. Okay?
Yeah.
All right. It's 12, almost 12:10. I think we need a 10-minute break. Go get some water or a bathroom break. So let's come back at 12:20. So that's 12 minutes. 12:20, be back. And if you want to stay, I'll be here and you could ask me more detailed questions. But I am going to get some water. Okay, I'm here.
Joanne, did you
Yeah,
see that you did civil engineering?
Yeah, my degree was in, my bachelor's degree is in civil, my master's in geotechnical, and I worked for a geotechnical engineering firm in Watsonville who's still here and hires our students. And most geotechnical engineering companies are geotech and environmental because a lot of times when you're working with soil, it gets contaminated, the groundwater is contaminated. So it's an advantage to have both in the company. So we did environmental sampling. I worked on a project in Watsonville. It was where the Santa Cruz County the Metro, they used to store their buses there. And we found out that there was contamination, both the soil and the water were contaminated. So
From the buses?
from the buses, from the fuel. So, and I don't know if it was the leaking from the buses or it was the filling up, because that's where they got their gas. It was probably an underground storage tank that leaked. That was probably it. I don't remember the details. But anyway, soil and water were contaminated. So we had to take soil samples in different areas, different depths. We had to take water samples, different areas, different depths, and figure out where the plume, it's called the plume of water that's contaminated.
Oh,
Because you have to make sure that it's like, removing cancer. You have to remove all the cancer. You can't leave a little bit left. So you have to find the
Yeah.
plume of the contaminated water and where the soil is contaminated. So we brought a backhoe in there and pulled out all the dirt, all the soil that was contaminated, and then laid it out in a certain area, and then introduced the process of bioremediation, which is putting microbes in. But I was involved in the soil sampling and the soil testing. I wasn't involved in the bioremediation, although I was working with an engineer from a company in San Francisco that was doing the bioremediation part. So that's what I did.
interesting.
Yeah. So, so for me as a geotechnical engineer, I needed to take the soil samples, I needed to bring it to a lab and test it, get the results, write up a report on what kind of soils, what kind of chemicals were in there. But I did not need to understand how bad the chemicals were, which ones were bad, which ones were not, and how to clean it up, because we had to hire another firm, which was called, and you might want to write this down, they're called Kennedy Jenks. Kennedy-Jenks. Kennedy Jenks. They're a big company in Santa Cruz. I'm sorry, big company in San Francisco that does environmental engineering. So they're the ones, once they got our report, they designed the system for doing the bioremediation. They were on site. I was on site. And then every week they would test the soil that was being bioremediated. I don't know if that's a right verb or not, to test how much the chemicals were, or if they were still in there. And once it was clean, then we put it back in. And that's where the geotechnical engineer came back in, because you can't just throw a bunch of soil in a hole and then build on top of it, because the soil will settle. You have to put soil in lifts and compact it, and then another bunch and compact it, and another bunch, because you want to make sure that if you put a building on top of it, the soil doesn't settle, right? So the geotechnical engineers came in at the beginning, then the environmentals, and then the geotechnical engineers came in the end. And then the same thing happened with the water. We did all the water sampling. We wrote up the report. And then, to tell you the truth, I was doing the geotechnical side. There was another engineer in my office who was doing the environmental, who did the water testing and the water report. And then it went to somewhere, and I bet you it was probably Kennedy Jenks again. And they probably designed the water thing, but I have no idea what they did with that. Maybe once you remove the soil, maybe the water gets better. I have no idea. But I do know they were continually taking soil and water samples to get it better.
I see. Yeah, I found their company website.
Okay. So that's a cool company. There are a lot of really big companies that do stuff like this. They're just not in our town. It's really a function of, and we'll talk
Yeah,
about
I'm not planning to live here. I mean,
Okay.
it's too expensive.
Okay. Well, San Francisco is just as expensive, but you could go to another place. But Crystal, remember how when I met with you guys with engineering education, I explained to you the differences between universities, so you could pull out a list of 15 reasons you would go to a certain university. Well, when we get to engineering employment, we're going to do the same thing. What are the different kinds of companies out there? Big, small. What is the advantages? Work for the government, not, So I
Yeah,
think you
I'm
had
interested in getting a government job,
Yeah.
whatever
Right.
I do, because those tend to be more stable
Yes.
and there's benefits from that. They may
Good.
be hard to get in, but it's hard to get out unless I really screw up.
Yeah.
If
Yeah.
that makes sense.
Yeah. And it's stable. It keeps you in one place, and you're also helping the community you live in. I think that's a big part of wanting to work for the government. And you could think every single city needs environmental, engineers. I mean, even city of Santa Cruz, which is relatively small, they have environmental engineers working in their water department, and the county does too. So I think there's a number of reasons to work for the government. The salary is a little better, the salary isn't as good as private practice, but you have more vacation, more holidays. The benefits are good and you're helping your community. So yeah.
I think I could also relocate if I wanted to, with a government job. Unless
Yeah.
I had to have a federal job, I guess.
That's right.
I'm
If you
not sure
got,
how that works.
that's correct. If you got a federal job, you could go to other places. That's right. And that's pretty cool too, the opportunity to travel. But
Yeah.
certainly if you work for the city of Santa Cruz, but if you work for the city of Santa Cruz and you have that experience under your belt, then another company, another municipality in another state would say, oh, she's already worked and she has experience working in the city. You could get another job working in the city. All right, I think I want to get off just for 5 minutes just to rest my voice. Okay, everyone? So I'll be back. Okay, everyone, I'm back. So we'll start in a couple of minutes and we're moving into materials engineering. Okay, I want to start in 1 minute. All right. I don't see Oscar. I don't see Tom. Oh, Thomas, I see. Thomas is here. I don't see Oscar and I don't see Alex. Okay. All right, we're back. I'm still recording and I'm going to share my screen. Okay, is everybody with me? Could I see some faces so I know someone's here listening? Thanks, Angel. All right. Thanks, Crystal. All right, so we're talking about materials engineering now. And again, ASM International, American Society of Materials. This is the Technical Society for Materials Engineering. So it's the same kind of thing. If you join ASM, you'll, as a student, which is, I don't know, free $10, $20 a year, you could get a magazine monthly, and then you'll learn more about materials engineering, all the cool things that are happening in materials. So it's really cool. All right, I'm going to start involving you guys now. And I'm going to go backwards because, well, maybe. Okay, I'm going to go. No, I'm going to just go from the middle. So Julio, you're on. So Julio, I wrote it here that says engineering materials. And there are 5 different types of engineering materials. So give me a name of a type of engineering material. So this is how I get to tell if you're here or not. Ken's, how about you? Kevin?
Sorry, can you hear me?
Yeah, I could hear you.
What was the question again? Can you
The
repeat it?
question is name a type of engineering material, a material used in engineering.
Concrete.
Concrete. Okay. Great. And I'm going to put that down here because it's an example. If something else. Okay, great. How about Kevin? So don't write this down yet because I'm going to put them in categories. Kevin, how about you? Give me another engineering material used in engineering. Okay, Luis C. Angel, could you check the chat for me?
Yeah.
Okay. All right, Luis C, give me another engineering material used in engineering.
We're gonna go with.
And I'm actually looking for 5 broad categories, and then I'll give you examples. So I don't know if that helps you.
The thing that comes to mind is just like biodegradable stuff, but that's not a material.
No, that's a property. That means it's a property of a material. You know, some material could biodegrade, and we can talk about that in a little bit. Come up with another one, Luis. What's your cell phone made out of?
Packaging. Glass. I don't know.
Okay, what's packaging made out
I would
of?
argue that what he said about biodegradable stuff is legitimate because it may not be worded that. It might be called, I don't know, alternative because of the plastic problem we have. People have to make those.
Yes, but I guess I'm giving you the 5. I'm trying to get from you the 5.
Oh, there's like categories.
The 5 textbook categories of engineering materials, and then we could talk about biodegradable. Luis, what's packaging usually made out of?
Paper.
Well, you guys are great. You guys are great. Okay, I'm gonna put down paper because we're gonna talk about paper in a little bit. But no, give me another big category. Okay, how about Luis Q?
Would it be wood?
Wood too. Another wood is under paper. So let's put wood over here. So I'm just going to put your notes that you're saying, and then I'll categorize it as we go along. Okay, Nathan, give me a main engineering category.
Metal.
Yay, metal. Okay. So one category of engineering material that engineers select from is metal. And it could be ferrous or non-ferrous. And what does that mean? Ferrous means that it has iron in it. So an example is steel. Steel is a ferrous material. A non-ferrous material has no iron in it. So like copper, copper, zinc. These are engineering materials too that are used that are metals, but they're non-ferrous. Everybody good? Okay, give me another category. Oscar is not here. Reed, give me another main category of engineering.
Glass.
Glass, great. And glass falls under the category of ceramic. So I'm going to write ceramics and glass. That's another category. And you could think of ceramics like, what are some examples? You know, tile, pottery. Okay, that's what ceramics and glass you use all the time. Okay, another category. So I'm up to Ruben. How about another? Luis C. said packaging. What is packaging made out of besides paper?
Plastic.
Plastic, great. And that is polymers. So polymers are plastics and elastomers, but I'm going to say rubber. So you guys know what plastic is. So polymers is the big category and includes plastic and rubber. So the soles of your shoe is a polymer, but it's rubber. It's very elastic. Okay, then concrete comes under another category, and I mentioned it earlier. So far we have metal, ceramics, and polymers. Those are three different types of engineering categories of engineering materials. Sam, do you want to take a guess what concrete comes under? And I said it earlier when somebody had asked me about new polymers. I said there's another material that's used a lot now, innovative.
Oh, yeah. Composites?
Yes, composites. And composites are a combo of materials. So an example is concrete. So actually, let me do it this way. Combo. So concrete is a composite. It's made of rock. Can you take a guess of what rock is? Is rock metal, ceramic, or a polymer?
I'm not sure. I would guess ceramic, maybe.
It's a ceramic, correct. And you could think about, I mean, you guys haven't taken a materials engineering class, so you don't know this stuff, but I'm just trying to, introduce you to and engage you rather than me talking all the time. You could think of pottery comes from clay, right? Clay is soil. Clay comes from rock. So rock is a ceramic. So concrete has rock in it, and it also has cement in it, right? Right? And what else is put in concrete? Rebar. Have you heard of rebar? Rebar is that metal that goes inside concrete. Did you ever see a concrete path, a concrete sidewalk being poured, or a concrete pillar being poured, or a concrete wall being poured? They always put steel in it, right? That is a composite. So concrete is a composite itself, but because the rock in there is a ceramic, but then rebar is a metal. So this is a composite. How about surfboards? Surfboards are made with epoxy and let's just say carbon fiber. There's certainly a different kinds of fiber you could put in there, but let's say carbon fiber. Epoxy is a glue, right? And a glue is a polymer. So I spelled that wrong. All glues are polymers, and a carbon fiber is actually glass. So I'm going to put fiber here. Okay, So far we have 4 engineering materials: metals, ceramics, polymers. I forgot to put a colon here. And composites. The last engineering material, which would be hard to like figure out what it is, it's called semiconductor. I'm going to put wood down below. We're going to talk about wood in a little bit. So semiconductor materials are materials that are not conductors. You know what a conductor is? Like electricity. It can conduct electricity. It can conduct heat. This isn't a metal is a conductor. It conducts heat. A polymer or a ceramic is an insulator. It's not conductive. A semiconductor is part conductor. Okay. And this is all used for making computer chips. You could see why now it's become its own category of a material. You know, there used to be, you know how errors, ERA, not mistakes, errors, ERA, errors in our past. Remember, there was the Stone Age, the Bronze Age, the Iron Age. All those ages were named because of the material that was founded, right? First, ceramics came around. Maybe I should put ceramics first, right? People would make tools out of rocks, right? And then once they got fire, I think there's a fire age too, but I'm not sure. Then they could find iron ore and they could make metal. And then polymers is very recent. It's like the early 1900s. And composites are more recent, putting combination of materials together. And semiconductors started when we started having like the Silicon Valley area. Okay. Now, notice that all of these are considered synthetic, artificial material. They're not naturally occurring, except for rock. If I put rock in here, yeah, rock is a ceramic and it's naturally occurring. But if I crush rock and make a powder, a clay, and then fire it and make pottery, pottery is a synthetic. Even though it's made with natural materials, it's really a synthetic. We had to make it. Iron, which is really steel, when you make something with steel, it's steel. It's not iron. Iron is the atom. Iron is the atom that you then put carbon in to make steel. So steel, even though it came from iron ore, which you could say are rocks, you had to process it in a certain way and add carbon to make steel. So steel is a synthetic material. But I agree that we could say there's a fifth material, engineering material, that's used a lot. I probably wouldn't say paper. Paper isn't used that much for large scale engineering, but wood certainly is. Wood is a natural occurring, just say natural, a natural occurring material that's used, but many times they inject chemicals in there, right? You've heard of pressure treated wood. It's wood that lasts longer. It's wood that's lasts longer, right? For posts of fences. Anytime you put wood in the ground, you should always use pressure treated. Fence boards that don't touch the dirt don't have to be pressure treated. So you could say wood is regularly natural, but once you pressure treat it, then you could kind of say it's synthetic. Synthetic. Okay, so I'm going to save that and I'm going to stop sharing for a moment. So that was, we touch on that. We have a whole course called Engineering 45 and Materials. We are just skimming the surface of what you cover in that materials class. All right. I love this. I find this really interesting because materials engineering is all about why do you select one material over another? Why is this cup made out of a ceramic? Why is the outside of this mouse plastic? Why is this glass on a computer screen called, do you guys know? It's a special kind of glass. Damn, I can't remember the name. Can anybody remember?
Gorilla Glass, I think is what they call it.
Yes, glass. Great, Zane. Gorilla Glass. It's a certain kind of glass. So I think that's really intriguing. Okay. In fact, look at this. I'll give you a stupid thing I did, which I guess we shouldn't say we're stupid at all, but I was stupid. I have shoelaces, right, that are black, and I wanted them to be colorful. And I love Guatemala. I've been down to Guatemala with the Engineering Abroad program a number of times. And I remembered going to Hart's Fabric in Santa Cruz, and they have this really cool colored fiber that's Guatemalan. So I thought, hey, I want to have shoelaces that are Guatemalan fabric. So I went to the store, brought my shoelace, measured it, cut out. I thought I wanted it for two pairs of shoes. So I cut out, I got enough for 4 shoes. Came home, I had this really long piece of Guatemalan cloth. I put it in my shoelaces. I put it in the shoe things, whatever. I went to tighten it, and what happened? It broke. Even though it's a fabric just like this, and it's made from cotton just like this cotton has a higher tensile strength, and it doesn't break because it's designed to be pulled. I'm not going to pull this because I no longer want to continue to break this. But if I just pulled this with the same strength, I would break it. And I was very disappointed, but I'm going to use it some other way. I'm going to sew it on the bottom of some black pants, and I think it'll be cool. Okay. So that's how to choose. Like, so why me? I'm teaching engineering materials. Why would I go buy something without finding out what its tensile strength is? Well, I didn't put on my materials engineering hat. I was just putting on the hat of being artistic, right? Well, we'll talk about a carabiner in a little bit. So does anybody have any questions so far about the types of engineering materials? So those are the categories.
Joanne?
Yes, Adam.
Brandon put a question in the chat that I think I also have.
Oh,
So things like
yeah, let me read it. I'm assuming wood and paper would belong to organic materials. Is that a category all by itself or a subcategory of something like composites? Okay, let me go back to sharing the screen. Okay, so these 5 are considered the main engineering materials. And then we could look at their chemical makeup, because the chemistry involved inside making these materials determines what the properties are. And I'll just give you some examples, although you don't have to remember this. Metals are made of metallic bonds. The metallic bonds have electrons floating all around. That's why they're conductive, both thermal and electrical. Ceramic has covalent bonds, and they don't have atoms floating around, so it's an insulative material. Metals have metallic bonds, so it makes it more ductile. We'll talk about all these terms. So we look at these properties. So when I look at wood, I know I'm moving in the direction of Adam and I forgot whose question. Wood is not put in one of these 5 categories, but in times wood behaves like a metal because it's strong. You could bend it and it doesn't break, but it also has properties like polymers because it's made of a bunch of fibers that are in line. Also, it could behave like a composite because there are these fibers that are encapsulated in something else in wood. So a lot of times wood is not a separate category, but it has properties of different categories. So when you talk about organic material, or I think we use the term organic material, but it's not considered an engineering property, but certainly you could choose in organic materials for certain things, like when Louise C. was talking about biodegradable material, right? Like ceramics doesn't biodegrade, but you could crush it up and put it in concrete or in asphalt. Glass, there are 2 different kinds of glass. I might be getting a little too technical, and maybe some of these questions I should answer outside, because my goal here is for you to just understand a little bit about materials so you could understand what materials engineers do. So I probably shouldn't be going so depth, but I'll say one more thing. Glass, there are some glass that's crystalline and some that are not. Some of it can't be recycled. So what you would do is break it up and then you could put it in asphalt. And that's why you might look on a street one time and you see it's kind of shiny. It's because they threw some glass in it. So I'm going to stop there in terms of materials. Okay. I'm going to the next slide.
Okay, thank you.
Yeah. Okay. What are materials used for in terms of industry? We talked about some already, you know, plastics, nylon is a type of plastic, neoprene is a type of plastic, and they're used for different things. Teflon is a type of plastic. If you ever put two pieces of pipes together, you use Teflon tape. Kevlar is a material that's used in bulletproof vests. It's also used in recreational vehicle. Liquid crystal displays are used on computers and on TVs. Transistors have materials in it that are conductive. They replaced vacuum tubes, which were a different type of material. Pyrex I love, I'll talk about in a little bit. Glass fibers, so optics and fiber cables that go underneath our roads. That's made of engineering materials. And then different types of actually materials on what you wear in clothes. Fabric is made from Gore-Tex, is an innovative material that's designed by engineers. Here, prosthetics and orthotics are braces and replacement for limbs. This is all using engineering material. It's probably a combination of metal, probably not steel because steel is rusty. It's probably metal that's non-ferrous, maybe titanium. There's also polymers here, so it could bend. It also might have some ceramic components, maybe. Okay, so if you're a materials engineer, you could work on lots of different types of materials, selecting materials for certain applications, and then also developing new materials. So the next thing I want to do is I'm going to go show you a video by Maceo. Maceo was an engineering student at Cabrillo who then transferred for Cal Poly and then went to San Jose State and for materials engineering for his master's. And now he's working in Santa Cruz on biomedical materials. So I'm going to stop sharing so I could pull up his slide because I've already opened all these videos. And sorry that you're getting those little advertisements, but that's the way it goes. Okay, I'm going to start.
Hi guys, and Carl has asked me to make this video for you about my education and career. So I'm a materials engineer.
Joanne, we can't see the screen.
You can't. Okay, hold on. Can you see the video right now?
No.
Okay, hang on. Thanks for telling me. Okay, do you see Maceo now? You guys?
Yes.
Okay.
Yes.
Okay.
Engineer. I work in the medical devices field, and I'm going to go through the questions that Carl has sent me and try to keep my time to the 2 to 4 minute window, and we'll see how this goes. Okay. I grew up in Santa Cruz. I went to Harbor High, and then I went to Cabrillo, and then I went to Cal Poly for my undergraduate degree, and then I went to San Jose State for my master's degree. Both my degrees from college are in materials engineering. How did I get interested in engineering, and how did I choose my field of engineering? The truth is I didn't know any engineers and had no idea about being an engineer, but one of my friends was going into engineering, and I have a little bit of aptitude for science and math. And after talking to him and then meeting Joanne and talking to counselors, it just seemed like a good fit, but I really didn't have a lifelong goal of being an engineer, and I didn't really know what it meant to be an engineer. And then materials engineering was just kind of, again, just serendipity. You know, I liked physics and chemistry, and I met the head of the materials engineering department at Cal Poly, and it just seemed like it seemed interesting, bonds and atoms and materials. And I wanted to work on wetsuits because I'm a surfer, and I spoke to a person at O'Neill's surf shop, and he said they had a materials engineer who worked in the wetsuits division. So I thought maybe that would work out. I've never worked on wetsuits, but I always thought that that would be cool. Yeah, so I told you which colleges and universities I went to and my experience at Cabrillo and transfer. So talk about your experience at Cabrillo and the transfer process. So Cabrillo was great. The teachers were very available for questions and helping me and really preparing me to succeed at Cal Poly. So the transfer process was scary for sure socially, because a lot of people had already formed groups at Cal Poly. So, you know, I'm not super outgoing, so it was kind of hard socially to transition to the new environment. But scholastically, you know, I had really gotten myself ready at Cabrillo and was successful at Cal Poly and graduated top of my class. Yeah, was pretty happy with that. So talk about your work as an engineer. I did a summer internship when I did my master's degree at a nitinol company that makes medical devices. I've worked at several medical device companies. The one I'm currently working at makes a device like this that's designed to catch debris and keep people from having debris go to the brain during heart valve replacement surgeries. So we have this device that goes over the aortic arch and captures debris and keeps it from causing a stroke in the patients. Like I say, during heart valve replacement surgery, if you want to go and watch what the procedure is all about and learn more about the device I work on, we have a website. It's www.emboline.com. And it's a pretty cool little video just to give you an idea of what our medical devices, what are they doing. And I think, you know, if you want to take the time to do that, that might be interesting for you. My favorite project that I've worked on as engineer, you know, I worked on a project that was for a clot retriever where we pulled blood clots out of the brain. And again, if you want to look at Stryker, the Trevo product, Trevo, there's tons.
I have these two sites on my PowerPoint slides, so you don't have to worry about spelling them or writing them down. Okay.
Of videos on YouTube and everything, and basically it's a mechanical thrombectomy device that goes in and is deployed in the brain, you know, in the vessels that have a blockage, and then you pull on the wire that's attached to the device and you yank out blood clots. So that was a pretty cool project that I was excited to work on. And again, you can look that up. It's already 4.5 minutes, so I'm going way over my time. Okay, how has engineering degree impacted your life, your quality of life? What opportunities do you experience? What we have experienced without the degree? So, you know, it's just been really fortunate for me that I'm able to afford a house and that my kids can eat healthy foods and that we can afford to live in Santa Cruz and again, own our house and do vacations and stuff. So, you know, having a decent paying career it makes a massive impact on your quality of life. I have children now, I have a wife, you know, I have a decent career where I'm treated with respect. I have health care. I can afford vacations. I have paid time off. It's massive, you know, and I work construction. I waited tables. My dad worked construction. My brother doesn't have a career going. So, you know, it's had an enormous effect on my quality of life and my ability to provide for myself and my family. So something to think about at your age and at your point in your life. One suggestion for engineering students, I would highly recommend internships and working hard. You know, you don't have to, I'm not super smart. I wasn't always getting, you know, great grades. I almost didn't make it to college. And was kind of messing around too much in high school and stuff. So my advice would be, you know, if you embrace your education and build relationships with your teachers and try to get an internship and do it for yourself, great things can come from that. That's what I believe. So it's worked for me. Sorry about the long video. If you want to send questions, Carl can relay those to me, and I hope you guys learned something. Okay, good luck.
Okay. Okay. So, yeah, and I think I got Cody involved to talk to Maceo on the outside to interview because Cody's interested in similar field to Maceo. But the hope is that you're, you know, learning from not just about the education path, but learning about careers and stuff. And that's why we're bringing in these speakers. And we can make them all live, but I know that Priti has brought in a couple of speakers live already. So I feel like I don't want to always tax my engineers because I'm already asking them all to meet with my students. So I figured if we already have a video that we taped Maceo, I'd rather just show the video. But if you'd like to get in touch with him, you could certainly talk, you know, get his information from me. Okay, I'm going to go back to our PowerPoint. You could see the PowerPoint, right?
Yeah.
Yep.
Okay. Yep. Okay. So here's Exponent, and this was a reminder for me. There is a really cool company out there called Exponent, and here's their website. And you could see that they're all around the United States. They deal with failure analysis. In fact, the company name used to be Failure Analysis Inc. And there's more than Exponent. There are other companies too. Whenever there is a failure in the United States with something, some bridge falls down, a car, you know, goes on fire, there's a little crack in some shuttle part, or, you know, this Challenger, whenever there is, a company like Exponent gets hired as expert witnesses to really investigate failure and then to be involved with the whole legal process. So somebody had asked me, well, how do engineers tie in with legal? This is one way they do. They hire only engineers who have PhDs. I did find one in the San Francisco Bay Area engineer who does not have a does not have a PhD, but he's kind of lucky. The reason why is that and you've seen so many probably law shows on TV or in the movies, you know, when they have expert witnesses, you know, like Joanne is the lawyer and I am representing some company where something broke, or some people who, you know, got hurt in something and there's a failure. Well, I'm going to hire an engineer who's an expert in failures of polymers, because it was a polymer that failed, to come up as an expert witness and put them on the stand and ask them why they think something failed, right? So because they're doing a lot of expert witness stuff in legal cases, they hire people with PhDs. But if this really interests you, like failure, and they hire PhD civil engineers, PhD mechanical engineers, PhD electrical, everything, because there are failures in many different things. They're not just physical failures. They could be some explosion. So they might need some chemical engineer. So this is a really neat company that I learned about a long time ago, and I wanted to share that with you. Another thing, so I'm kind of pulling out things that I think are really interesting, that I find exciting. This one also, evolution of materials and products. You know, you look at any product, and many sports products, there's a transition. I mean, you guys weren't even around when people were using wooden tennis rackets. When I was a kid, I had a wooden tennis racket. Well, it moved from wooden, and then they thought aluminum would be better, right? And now they're made out of carbon fiber, right? The transition in material choices is based on what materials are available and what their properties are. They're all ductile, but they're also all stiff. But these are better. They're more impact resistant, which we could talk about impact later, than the wooden ones. The wooden ones shake too much. This absorbs more energy, kind of like a rubber ball absorbs a lot of energy.
I happen to have been old enough to have had a wooden racket myself.
Thank you, Cody.
They were
Thank
also
you.
much heavier.
And they're heavier, right? This is more lightweight. This is a very important thing. Getting materials to be more lightweight. Thanks for adding that, Cody. Okay. So now let's see how materials and chemistry combine. I've talked a little bit about how they do, but here it is. Materials is really labeled MSE, Materials Science and Engineering. You get a degree in a materials engineering degree, but you're learning about the science. Engineering is why things behave the way they do. No, I'm sorry, how. Hang on, let me put it in here. How materials behave. And the science is why they behave that way. So in order to understand how a material behaves, the engineering part, we need to understand the material science. And what is the material science all based on? It's based on chemistry, right? So if I know the composition of a material, if I know what it's composed of and I know its structure, I can know its properties. Remember we talked about graphite and diamond? They're both have the same composition. They're both made of carbon, but their structures are different, which leads to different properties. Or go back to, what was it? Ethanol and vinegar. They're both made of carbon, hydrogen, and oxygen. Their composition, the atoms are the same, but the number of atoms are different and their structure is different. So it gives us different properties. And once we know the properties of a material, then we know how it's going to perform, and then we could choose its application. Okay, so for instance, if I had been when I was in that fabric store, if I had been there and actually pulled it apart and tested it in tension, I would have found out that its tensile strength, it does not have good tensile strength as a property, and it's not going to perform to be used as a shoelace, and I can't use it as a shoelace. But I didn't do the test when I was there. Okay, then in addition, I put it a little bit away. Even though we know the composition and the structure, we could process the material in a different way to change the composition or structure. So for instance, and again, I might be getting in too much detail, but steel is an amazing material, steel, because it's cheap, it's readily available, it has a ton of properties, and I could tweak it. I could process it so different to get something different. If I process steel, which is iron with carbon, and put more carbon in, I'm going to make it harder. If I put less carbon in, I'm going to make it softer. See, and that helps me. And sometimes I need a harder material, and sometimes I need a softer or a more flexible material. So this may be a little bit too theoretical for you, but I have another video that Carl made that looks at eggs that we eat, and shows how you could process eggs in different ways and get different properties. Okay. All right. So let me go to that. I'm going to stop sharing again. Here it is. Okay. Okay, do you see Carl's face here?
Yes.
Okay. All right, let's move the volume up to begin with.
All right, everyone. I just wanted to do a short little video on this concept of processing, structure, properties, and performance. So if you recall, I've been talking for a while that a lot of material science, kind of comes down to this idea that how you process something will lead to different kinds of structures. And those structures lead to different kind of properties. And remember, properties are just kind of behaviors. And those can lead to different performance characteristics. And performance can be more than just, like a property might be very isolated to a single thing, and performance can be a more general assemblage of different properties that come together in how the whole material behaves. So we don't really have enough knowledge of all of material science yet to kind of delve into this for a kind of formal material system. So what we're going to do today is think about something that a lot of people have eaten before, that has a lot of variety and how this process plays out with it, and that is eggs. So if you go through and think of all the different ways that we can basically eat or use eggs as human beings, right? Some people eat them raw. It's unusual, but it happens. We have boiled, and boiled eggs can basically run from soft to hard. We also have poached eggs, and poached eggs can also kind of run from soft to hard. And then of course, another would be scrambled. And if you really delve into it, you'll find that there's other ways as well. You can make baked eggs. Quiche is an example of a kind of baked egg dish. And that leads to a bunch of different structures. And so to kind of address the structures thing, let's jump out over to the web. And so we'll come here, and I just did a Google search for boiled eggs. And you can see I set up a variety of tabs here. And the first one we want to look at is, as you cook eggs, here you can see a 6 minute, 7, 8, 9, 10, 11, and 12-minute egg. And you can really see how the kind of structure changes, right? You have a very soft structure of the yolk to one that's relatively hard. Then we can go on to another tab here. This is looking at poached eggs. And you can see here's a poached egg with 2 minutes of cooking, 3 minutes, 4 minutes, and by 5 minutes, you start to see the yolk solidifying. And then let's just take one look at scrambled eggs. And here's an example where, they're looking at the different kinds of textures and the different things that result from being cooked in a microwave, whether you beat in some air into the eggs, whether you start the pan cold or you start the pan hot. If you add extra yolk, you can actually poach scrambled eggs. I hadn't ever done that. Or if you add some cornstarch, you'll get these different textures. So the idea is that these structures, the way it kind of ends up resulting is what I would say is akin to the kind of structures that we see with materials. And then from there, we can get in and start articulating some of the properties. So you might say that those eggs are runny, or they might be considered delicate. Right? You might think of them as being rubbery. You might think of them as being spongy. Sometimes I've had some scrambled eggs that I would say seem like they were kind of slimy. Fried eggs where they're a bit crispy. And even some boiled eggs where the yolk seems sort of powdery. And so there's just a variety of ways we might describe those structures and the way that they kind of, the way we describe them using words. And then that leads to different kinds of performance. So for example, are they good both hot and cold, for example? Some are good hot, some are good cold, and maybe both, or maybe one or the other. Another kind of like overall performance thing would be how it travels. It can either travel well or poorly. So for example, you probably wouldn't make a soft poached egg and expect to bring that in your lunch. But a hard-boiled egg might work out just great. And then if we think about another kind of performance of this whole process, or this whole kind of procedure of going through this, like some processes are scalable. So for example, if you are cooking for 12 people and you all want to eat together, you might go for scrambled eggs because you can cook easily a dozen scrambled eggs all at one time. Whereas if you're going to make those poached, it might be quite tedious to try to get through that whole process. So I hope this gives you a good idea of how this plays out in a it's certainly a material system, eggs, but we're just more familiar with it in terms of the kitchen and in terms of eating. So thank you.
Okay, I'm going to stop sharing. Ah, meringue. Yeah, this video is making me a little hungry. Yes, I agree. Okay, we'll take a break in a little bit. All right, so I think that was such an awesome analogy of looking at how a processing of a material could impact its properties and its application, because we're all comfortable with eggs. When you do take the Engineering 45 Engineering Materials class, we're going to delve into all this using materials, and it's a really amazing class. We break things and everything. All right, so I'm going to go back to my PowerPoint. So I'm going to share my screen. Or any comments besides what's in the chat? Okay, so let me go and share my screen. So I'm back to the PowerPoint, and this was the egg thing. And now the next thing I'm going to show you, hang on. Okay, so the next thing we're going to look at is properties. Okay, the material properties. And the properties are really how a material responds when it's subjected to a stimulus. And what do I mean by stimulus? So you have a certain material and you subject it to something in the environment. And when you subject it to that in the environment, whatever it is being subjected to is a stimulus. So for instance, let me do this, and we're going to keep going along the names. So when you want to determine its thermal property, how conductive it is with temperature, let's say temperature conductivity, and this of course is electrical conductivity. Let me say conductivity. You have to subject it to heat. The only way for me to know how a material, what its thermal properties are, is if I subject it to a stimulus, and the stimulus is heat. Okay, so what about, who am I up to next? Thomas, did you go already? Or Sam? Sam, Thomas, or Ulysses? I'm not sure where I am.
I haven't gone.
Okay, and who are you? Thomas. Okay,
Thomas.
Thomas. So in order for me to test its electrical conductivity, what do I have to subject the material to?
To electricity.
Right.
To electricity.
Yeah. Electricity.
Okay.
You could say electricity. You could say maybe not conduction.
A current.
A current. Right. Thank you. That's what I was looking for. Like you could say electricity, or you could say a current, right?
Okay.
Okay. How about magnetic? In order to see whether something's magnetic or not, how do I determine whether it's magnetic or not? And this is kind of another giveaway, like the second one. So Ulysses?
You can either use magnets or metals
Right.
to see.
Right. That's right. Just use a magnet, because some metals are magnetic and some are not, right? So if you have if you have a magnet and you subject it to a metal, you could determine whether that metal that you're subjecting it to is magnetic or not. Okay, how about Zane? What about how can we check out its optical properties, whether it's shiny or dull or whatever?
Shining a light on it.
Yes, light. Exactly. Okay, and then the big one, which Carl talked about a little and I was talking about, is a mechanical property. And a mechanical property, the stimulus is a load or a force. They're synonymous. They're the same thing. So if I subject my hand to the fist, a load, I could determine what its mechanical properties are. If I take a pen that's pointed and I put it in my hand, I'm applying a load and I could determine what kind of mechanical properties it has. Okay, so these are 4 different types of properties: thermal properties, electrical, magnetic, optical, and mechanical. And then the last one is chemical properties. And chemical properties is basically subjecting it to some kind of chemistry or environment that causes a chemical change. For instance, you know that probably steel corrodes, right? You put a piece of steel, it's subjected to rainwater, and it's eventually going to get corrode. It's going to rust. It's going to corrode and it's going to get rusty. Okay. So when you have a material, when subjected to a certain environment and it has a chemical change, with corrosion is a chemical change. The water is interacting with the metal and it's creating something, a ferrous oxide, an oxide that is the rust. Okay. So there are really 5 chemical properties. But what we're going to work on today and have an activity for today is a mechanical property. Okay. So I'm going to the next slide. In order to put a load on something, and actually I'm gonna stop sharing for a moment. Again, I want to see faces. If I could see faces. If I put your 2 hands together and try to pull them, when you pull something, it's called tension. So just like I took my shoelace and I pulled it, it's called a tensile force. That's the kind of force I'm applying. How about put your 2 hands together? When you press, that's called compression. That's also loading something. I could take the cell phone and I could bang it, right, in compression. I certainly wouldn't want to bang it too hard because the glass will break. And you know how many phone glasses have broken, right? But this is compression. So tension, tension and compression. Then there's torsion, twisting. Try to twist something, take something, and you're going to be doing this in the activity together. Torsion, applying something in torsion. I mean, a plastic, I could probably spin around, right? But something that's brittle is going to break. Okay. So tension, compression, torsion, and the last thing is bending. Bending. And I'm going to go back to sharing.
What about shear?
Shear. I didn't put shear on here, but shear is another good one. I'll write it on here, but I didn't cover that one because I'm only going to have you do these today. But shear is another thing where you're trying to break. You have 2 pieces of wood and you have if you have 2 pieces of wood and you have a screw and you pull the pieces of wood, you can shear the bolt. It's a little more complicated. We're not going to talk about it. So here you're seeing this is tension, it's pulling. Here's compression, pushing. Here's torsion and a twist. And here's bending. And notice there are 2 different kinds of bending. One where you support it on both ends, and that's called simply supported, and you put the load in the middle. So you can imagine this is a bridge. And this is called cantilever. When you see signs that are sticking out from stores saying their name, and they're only connected at one end, this is cantilever. Okay, so these are called loading conditions, how I could put a force on something. And now we're going to the next slide. Everybody still with me? Okay, so we are looking at only 5 properties, 5 mechanical properties. And there are more, but we're just going to look at 5. So hard or soft, you guys know what that means, hard or soft. It's the ability to be indented. Can I scratch it? Can I put an indentation in it? Next, stiff or flexible. Can I bend it? This fabric is flexible, but the glass on this phone is not flexible, it's stiff. So these are opposites. Hard or soft is an opposite. Stiff or flexible is an opposite. Elastic or plastic, and this you may not know about. So I brought some candy, which I'm making you even more hungry now. I have an airhead, And actually, let's go through this and then I'll do it with the bigger screen. So elastic is the ability to return to its original shapes. You apply a load to it. A good example is a rubber band. You pull a rubber band and then you unload it and it goes back to its original shape. And that's what elastic is. Plastic is the opposite. You pull it and it stays stretched out. Ductile or brittle, you probably know the term brittle. You take something and you bend it like a piece of chalk and you bend it and it just breaks, it pops. But if I took something else that was softer, I could bend it and it's ductile. I could pull it out, it's ductile. And the last one is strong or weak. And I think you know what that is, strong or weak. When does it break? What's the maximum stress I need to break it? But what's interesting is not only do these properties have to do with which material it is and its chemistry, it also depends, am I loading it fast or slow, right? How does that affect ductility and strength? We'll talk about that in a little bit. How about when it's subjected to an environmental condition? How about if it's hot or cold, right? Or it's dry or it's moisture or has moisture. So I'm going to stop sharing. Okay, and what you might want to do is put me, I don't know if you see me with everyone else, but you might want to put me in the view where you just see me. Okay. So what I have here is an airhead. Actually, I'm going to put mine bigger too so I could see myself better. Okay. So I have an airhead, which is basically taffy. I don't know if you've ever had it or not. But I have an airhead. And I'm going to put a tensile load. I'm going to pull it. So would you say this is ductile or brittle? Go back to the definition. Ductility is, wow, it smells really good. It's ductile. Everybody good with knowing that it's ductile? Because ductile and brittle, ductile, it could be pulled out or bent, right? I could bend this. If I had chalk, I wouldn't be able to pull it out. Now let's look at, right, here's a Twizzler. Also smells good. It's harder to pull out, which means which one's stronger? Is the Twizzler stronger or the taffy? It takes more for me to pull and break it than the taffy was easy to break. So which one's stronger, the Twizzler or the taffy? You guys, I need Twizzler. Why don't you all get off of mute? Everybody get off of mute. Okay. So the Twizzler took me to, I had to pull harder, pull more than I did with the taffy to break it. So the Twizzler is stronger. It's stronger and this is weaker. So whenever we talk about these material properties, we're really comparing two material together because certainly the Twizzler is, it's stronger than this, but it's not as strong as my shoelace where I could pull it and I can't break it by hand right now. So which is stronger, the Twizzler or the shoelace?
Shoelace.
Shoelace. Okay.
Oh, that's shoelace. Oh, never mind.
Okay. How about we have a lab in our materials class called Materials from the Candy Shop. So here I have a candy cane. It's very hard to pull it, right? So is it stronger? Which is stronger, the Twizzler or the candy cane?
The candy cane.
Candy cane. Okay, when let's do a different property. I take the Twizzler and I can bend it. What happens when I bend the candy cane?
It breaks.
It breaks and a piece of candy cane flew.
Hopefully not on the carpet.
It's on the carpet, but it's not where the applesauce is. Okay, so which one is ductile and which one is brittle?
The Twizzler is ductile.
The Twizzler's ductile. Yeah.
Twizzler's ductile and the candy cane is brittle, right? Okay. Okay, I'm gonna give you some environmental now. This Twizzler is new. I just opened the package. I could pull it. It's pretty ductile, right? But then where did I put it? We save like Twizzlers. I must have left it in the house, so I have to go and get it. But I have this old Twizzler, so I'm gonna have you tell me when we have that one. Okay, here's another thing, another material property. I put this airhead on top of my heater. So here I'm now subjecting it to an environmental condition. Is it going to be softer or harder than the room temperature one?
Softer.
Softer.
It's going to be softer, right? It's actually pretty sticky. I don't even know if I'm going to be able to take it off the wrapper. See how it's coming off the wrapper? It's very ductile. Look at this. Look at how ductile this is. Way more ductile. Sorry. Way more ductile than this one. So temperature really controls the properties too. All right, hang on. I know I'm now making you hungry for candy. And if we were all in person, we would all be doing this with candy at home. I mean, in school. Okay. Gummy worms. Here's a gummy worm. When I squish it, what happens?
It compresses.
It returns to its original form.
Right. I'm compressing it. It returns to original form. So is it elastic or plastic?
It's elastic.
Elastic. And if I pulled it too, I pull it, it goes back to its original form. It's elastic. Certainly if I pull it too much, wow. But it does still bounce back, right? That's elastic. The taffy, the airhead, is this elastic? As soon as I pull it, it stretches. What is it?
Plastic.
Plastic.
Deformation.
Plastic. So this one's elastic because it bounces back, and this is plastic. All right. So let's see what else I have. I have to get you more because I have an airhead and gum in the freezer. So I have to go get it. But we could look at gum compared to our taffy. It's really brittle. You know, when we think of gum, it's very soft, it's bendable, but it really is a little more brittle. And this is room temperature. Here I have gum. Also, I put on the heater. Oh, this, I just bent it. Here, this one's going to be a little more ductile because it's warm. And I got juicy fruit. But now, okay, so what do you think's going to happen if it's in the freezer? Let me stop for a minute. And, oh boy, no, I don't want to do that. I want to share the screen. Okay, so hard or soft, I know you knew before. Stiff or flexible, you definitely know that too, right? Yeah, stiff or flexible. And then elastic or plastic, you now know that. You probably weren't used those words interchangeable before, but now you know the real definition. Elastic means it could come back to its original shape. Plastic is permanently deformed. That's why a lot of what's the Spanish word for Play-Doh? Plastina, isn't it?
Yes.
Plastina? It's
Yes.
called plastina because it's plastic. You take Play-Doh, you mold it, it's plastic. It's not elastic. It doesn't bounce back. Oh, maybe clay. Clay, I think might be. What's clay called? Is that what's called plastina? I'm not sure. But anyway, but elastic, just think of a rubber band. You pull it, it goes back. Okay, ductile or brittle, whether you could draw it out or not. So chalk is more brittle and ductile is you could stretch it. So so the gum is really, it's more brittle, you know, until you put it in your mouth, you process it. Hang on. I'm processing it. I'm adding moisture. Are you enjoying this? Probably not.
Yes.
Okay. But juicy fruit is so juicy that when I take it out of my mouth, it's
Do
more
you have
ductile.
stock in any of these companies, Joanne?
What was that?
Do you have stock in any of these companies? you guys
No,
know?
no. I tried to pick ones that I don't like because then I won't eat the whole bunch. But you see how when I added moisture, I added an environment, it made it more ductile when it was brittle before. Okay. Oh, I gotta take this out. Sorry. Don't look. Okay. Sorry. Okay, so now you're comfortable with this. You kind of understand the environmental conditions, but let's think about composites. Oh, so when it's in the freezer, I probably don't even have to go get it. But if it's in the freezer, is it going to be soft or hard?
It'll be hard.
Harder. Is
Hard,
it
yes.
if it's cold, frozen, stiff or flexible?
Stiff.
Stiffer.
Elastic or well, it's going to just break. Really, this doesn't apply. Is it going to be ductile or brittle?
Brittle.
Brittle. Okay. And strong or weak? That's a really good question.
I'm gonna say weak.
Probably weak because it's more brittle,
Yeah, like,
right?
it's gonna shatter more likely than if you just
It's
drop
gonna
the piece of-
shatter.
Yeah.
Yeah. Although ceramics are not good in tension, but they're very good in compression. So ceramic material is not strong in tension, but it's very, very strong in compression. Hang on. Okay, the other thing I wanted to talk about is, well, 2 more candies. I should have brought a plate. Because
Joanne, you're still sharing the screen if you wanted us to see what you're doing.
Oh, okay. Yeah, hang on. I'm getting the plate off my heater so I can put my food there. All right, so I'm gonna stop sharing and you could see me again, right? So M&Ms. Which type of engineering material category do you think this goes under?
Chemistry.
Metal, ceramic, polymer, composite.
Composite.
Composite. It's a combination. It's a combination. It has the hard shell on the outside and the soft chocolate on the inside. Why does it have a hard shell?
It doesn't melt on your hand.
Right. What is that? Isn't that melts in your mouth, not in your hands, right? Do they
Yeah.
still use that same saying? Isn't that a property? It's a property. The reason that you combine materials is because it gives you 2 different properties, right? So that's this. It's actually has pretty good compressive strength, which is pretty funny. And this way it even has more compressive strength. So it's stronger. It's hard on the outside, but the inside, of course, is soft. All right, well, what about a Kit Kat? Oh boy, I'm gonna make a mess. So I have a Kit Kat. What's gonna happen when I bend this? Oh, is this a composite?
Yes.
Yeah, why? What's in here? Chocolate? I think it's wafer. So let's try to give it a bend test. I'm gonna do it on the closer to my table so it doesn't go all over. But you'll see that it just broke, clean broke. So is it brittle or ductile?
It's brittle.
Brittle. So the wafer in the middle is brittle, right? So wafer is brittle, but chocolate is more ductile. But chocolate can't really stretch that much. The more of the these other kind of candies are the ones, oh boy, it's stuck to my paper, that can stretch. Okay, so hang on, let me just rinse my hands. Okay, my hands are clean now. I can touch the computer. All right, and I'm going to shut the heat off in here because I had the heat on so I could get warm things. So I don't think I need to go get the cold stuff, right? You know what's going on. So I'm going to share my screen again. And so that's what we're looking at. And the next page, I made up a table here that we could have filled out, but I don't think we're going to because I want you to do an activity. But basically what I did is I'm showing here are all the properties. Strong, hardest, soft, strong. Sorry. hard or soft, stiff or flexible, elastic or plastic, ductile or brittle, strong or weak. And we could have went through these candies and determined which one we think they are in comparison to each other, but we're not going to do that. Okay. Now we're going to do a class activity. Okay, so we could take a break first and then we could do a class activity. So I'm going to stop sharing here and I'm going to go back to the module. Where is the internet? Nope, that's not where I want to be. Share screen. And I'm back to our module. So the Chem-E, Mat-E class slides are the PowerPoint slides we've been watching. And then of course, the one that's posted doesn't have the materials and stuff in there. So after tonight's class, then I'll go in and put in the new one that has the different types of materials. So here's our activity. Okay. So I'm going to open that, which I believe is right here. Material activity. And this is what you're going to do. This lab is kind of a scavenger hunt where you're going to look for things in your house that exemplify a given mechanical property's extremes. You will work in teams of 3 or 4 in Zoom breakout rooms. So what you're going to learn, one, you're going to explain the difference between these material properties that I have listed here, make sure that everyone understands it. And then you're going to connect each property with a behavior of a real world object. So what you're going to do. You're going to be in your breakout room and you're going to talk to the classmates in the breakout room about the following properties and the descriptions and see how you think about them and talk about them in a different way and dig into play. Basically, I want you to talk about it so that everybody understands what they are. And you might have different understandings and share that. And then for each property, you're going to run around your house and you're going to find something that shows the property's extremes, so high and low. So for instance, when your group is ready, you're going to run around the house and find something hard and soft and bring it to the breakout room. You're going to find something stiff and flexible and bring it to a breakout room. And then elastic and plastic, ductile and brittle, and strong and weak. And actually, and then say, okay, which were the best examples of the properties? What you're going to be doing is more what an engineer does than playing with candy. So maybe you might be a little disappointed that you didn't get to play with candy, and you can if you want after this class. But you're really looking at real world objects and what engineers chose for materials. Okay, so everybody knows what they're going to be doing. Okay, I'm going to stop sharing. Let me open up the view of everybody. I got to open up the door. It's so hot in here. Okay. Okay, so everybody's here now, and we still have 40 minutes of class. So let me just check for a minute, because we are going to do I want 10 minutes at the end. So what I think, well, I guess I could just ask you guys. I mean, how much time do you think you need in a breakout room? 15 minutes, 20 minutes?
Yeah, 15 minutes should be good.
Okay, 15. Do we want to do 20 just in case? Because it's nice to get to know each other. You guys are not sitting in the same room next to each other. So let's take a, now we only have, yeah, let's do 15. We'll take a 10-minute break in 15 minutes. Or do you want to just go, do you guys need a break, or can we just go into the breakout rooms and do this? Because while you're running around, it's going to be like a break. That's what I'm going to do.
Yeah,
I'm going to put you in your breakout room. And what's going to happen is at 2 o'clock, you're going to come back in. Okay. So everybody's going to come back into the main room at 2 o'clock, which I think I can control. So you're going to come back at 2 o'clock and we'll have the last 10 minutes together. But so from now to 2, meet your people in your group, go run around, take a little break, come back, talk about the stuff. All right. So let me set out the breakout rooms. Actually, how many people are we here today? 4 by 6, that's 24, 24, 25, 26, 26. Let's say 3 or 4 people. Let's do you want 3? Let's do 4 people. 3. Let's do 3 people. So about 3 or 4 people per group. Okay. So breakout room, sign automatically. I want 8 rooms. Okay. Okay, I'm opening up all the rooms now. You're either in groups of 3 or 4. Go for it. And I'll see you back at 2. And I'm going to stop recording right now.
You just share it in the chat.
Yeah, so I'm just gonna, I didn't record that part, but we just watched a little video on material properties. And if we go back to the PowerPoint, there's a place that I have, well, what about if you apply something faster or slower, or you know, you see how when he put down the lead, he kind of just dropped it on there. That's more of an impact load. It's an instantaneous load rather than a gradual increasing load. So material properties aren't just the function of the material itself, but it's how you load it as well. So I'm going to, now the last thing I want to do is just look at our module. Let's see if I could get back here. Yeah. So I'm back at our module. So the material selection video is right here. And now the homework is typical. You know, you read a chapter and then you do a quiz. But I want to show you what this last homework assignment is, this discussion. And so I want you to watch 2 more videos on chemical engineering and just write 3 sentences about what aspect of chemical engineering interests you. It's quite possible that chemical engineering isn't that interesting to you, but there must be some element in there that's interesting. Work in a big plant or whatever. And then I want you to watch a materials engineering video and do the same thing. What's about materials that's interesting? And then I want you to watch Isadora's video. And what's interesting about Isadora is she transferred from Cabrillo to San Jose State, got her bachelor's degree in chemical engineering, and decided she really didn't want to work in chemical engineering per se. She really wanted to go into sales because she's really a people person. And she took some business classes. So she wanted to combine her chemical engineering knowledge and technical knowledge with her business courses and with being social. And then I mentioned, fun fact, she met her husband in the Engineering 5. And then the last part of it is a hands-on activity where I'm going to have you choose one item. And the example that we have here is a scissor. And I want you to look at that item, think about its performance, and talk about, well, why did they use metal here? Why did they use a polymer here? And the description here. And here are some examples. So for a scissor, there are some reasons why they might have chose that. Okay, so I'm going to stop sharing now. So that's a discussion post where you post to the discussion. I'm not requiring you to respond to somebody else's, so don't worry about that. Okay. Well, we're at 2:10 now. So I'm going to, do you have any questions? Just ask you questions. Do you have any questions for me? No? All right, so next week, you're going to see Priti because you're going to be doing mechanical and aerospace, mechanical, sorry, and biomedical. So you're going to do a hand project. It's really fun. Mechanical hand project. And then I'll see you in 2 weeks, and then I'll see you in 3 weeks. Okay. All right. So I'm going to